All right, now we are still under the exponent unit, but now we're dealing with square roots. Now, square roots don't look like exponents, but they actually are. They're actually fraction exponents. There are square roots, there are cube roots, there are tons, there's an infinite number of fractions, but we're only going to be looking at one fraction, and that's a half. Now, if you have something like x to the power of a half, we say that that is the square root of x, and there's a little 2 there, and that's because there's a 2 down here. If I asked you for the cube root, or x to the power of a 1 over 3, I would write that as the cube root of x. Because of the 3 on the bottom, there's a 3 right there. If I had x to the power of 1 over 4, I would write the 4th root of x, the 4 and the 4. So because I write a half here, because there's a half there, I write the square root symbol with a little 2 there, except that we don't actually need to write the 2. We can just write it without the 2, and that assumes that it's going to be a 2. So you've already seen square roots before. The square root of 9. Square root of 9 is just 3. Normally, we wouldn't write this, but actually we would write this as the square root with the 2 there. But again, we don't need to write that. We can just leave it like that. And the square root of 9, like I said before, is 3. So we're still dealing with exponents, but you just don't see it. Like this. What is 16 to the power of a half? That doesn't, I've never seen that before. However, we could also write it like this. Square root of 16. They mean the same thing. And the square root of 16 is 4. The square root of 25 is 5. The square root of 169 is 13. So when you're looking for the square root, you're thinking, what number times itself is 25? Well, 5 times itself, or 5 times 5, is 25. So the square root of 25 is 5. Now, there's some stuff here that we don't need to go over right now. It'll make more sense later. Let's just try the very first example. So, what do we do if the number is not perfect? So what we mean by that is the square root of 100, well, that's just 10. 100 is a perfect number. It's 10 times 10. The square root of 64. 64 is a perfect number because it's 8 times 8. So square root of 64 is 8. So I'm trying to think of a number that can multiply to 12, and that number is exactly the same. So 12, I know 6 times 2 is 12, and 4 times 3 is 12, but we're looking for both of the same numbers, and that's impossible. You can't actually do that. And that's what it's saying here. What happens if it's not a perfect number? What if it's not a perfect number? Well, we can reduce it, we can simplify it, and we use these prime factorization trees that we've been using, I think, in the previous unit, and we are going to use again here. So 12 is 4 times 3. 4 is 2 times 2, and we can carry the 3 down. Now what we're doing is we're just looking for pairs. And there are a pair of 2's. Just like in the square root of 25, that was 5. It's because it was 5 times 5. It was a pair of 5's, and the answer was just a 5. Here we're looking for any pairs. We do have a pair of 2's, so we can take a pair of 2's out, and then whatever's left over stays on the inside. So this is considered simplified. I couldn't make it it's not going to be perfect. The square root of 25 is just 5. And there's no square root symbol there. There will always be, when we're simplifying here, simplifying a non-perfect number, there will always be some sort of square root symbol. So let's try the next one, 28. So that can be 7 times 4 or 14 times 2. So I'll try 14 times 2 for no reason other than just 'cause. This 14 is 7 times 2, and you can carry this 2 down. those are all prime numbers. You can't reduce them anymore. Is there any pairs? Yes, there are. There are a pair of 2s. So you can take 2 out, and you're left with just a 7. Moving on, 50. That's going to be 5 times 10. And 5 can get carried down. 10 can go 5 times 2. There's a pair of 5s, so you have the 5 on the outside, and the leftover is just a 2. 99. 99 is going to be, I guess, 9 times 11. 9 is 3 times 3, and you can carry down the 11. There's a pair of 3s, so 3 comes out, and the leftover is in there. Just the 11. So I'll zoom out here. I know I did a lot of talking at the beginning, but the idea here is we're going to use the prime factorization trees. Any pairs, we'll take out a pair. Notice that even though when I took the 2's out, I didn't write 2 times 2 out in front. I just wrote a single 2. Here, I didn't write 5 times 5 out in front to be 25. I just wrote a single 5. And that will always be the case.